All right, so the weekly 385 just finished. And I did pretty well. Actually, completely didn't finish. It's still going, but I just finished. And I did pretty good. I'm going to absolutely release this after it does finish. So, but I figured I'd go through the questions. I haven't done that in a while, and it's kind of fun. And after looking at this rating, I'm like, you know what? I am qualified to talk about the solutions. So it's the oldest trick in the book when they do this cheeky, there's two questions and they have the exact same prompt but different constraints, to kind of like figure out one of them and then just copy paste your solution to both. Like make sure that the time complexity is enough to finish both and then copy paste for both. So here the constraints are quite stringent. Here it's very simple. So here what you could do is you could just compare every single word and use like Python dot starts with or something like that and dot ends with. But the time complexity of that is quite bad. It means you have to go through every word. For every other word, you'd have to go through every other word. So it's already O of n squared, where n is the length of words. And then for every word, you have to compare the length of those words as well. So it's O of n squared times m, which here would be O of 10 to the 15th. So you have to actually reduce like two of those. I guess it'd be a little bit less than that. So what I did here was just I copy pasted my little string hashing algorithm that I have made in the past. The idea is that you hash the string into a number. So given any string, you say this is now a number, and whatever characters in whatever order is going to determine exactly what that number is through all this complicated math revolving around a really, really big prime number, among other things. And then now we have this way to refer to a string as its hash value and then just compare those. So for example, like PA is going to have a different hash value than PA. But if there was another PA, such as like if we were comparing it to the first half of this, then it would have the same hash value. And that's like the second part of this little class, is to be able to query not just the hash value, but any hash value of any substring in O of 1 time. That's like a prefix hash or a rolling hash. People also kind of use that term. So the idea is the first thing I do is I just say, okay, words are now numbers. Everything's a number because it makes it simpler. Importantly, I don't say ord C minus 97, which is really common in Python and I think other languages. This maps like A to 0 through Z to 25. The minus 96 maps A to 1 and Z to 26. So it's one indexed, which is a little confusing, but the way the hash math works out, that leads to less hash collisions. And hash collisions are if you had, like, let's say this happened to the one in a billion chance happened to map to the same number that this maps to. It makes that nowhere near as likely on a small scale. But anyway, so that's the first thing I do. I turn them all into numbers. It makes it easier to turn it eventually into the hash prefix or hash number. And then I just go through and I say, well, actually, this is my code I sort of workshopped to work for Q4 as well. So what I really do, actually, this is kind of the complicated solution. What I do is I say, okay, find the prefix hash array. So this is the thing I can query for any number representing any substring. Create that for the given word. Find the hash for the entirety of the word. This is just kind of like, not necessary, but shorthand to declare this variable. And then for every single index in the word, try that as a prefix / suffix. So for example, if we're looking at ABABA, try just the first and last. Like two, okay, they're both A, so that actually works. So because the prefix and the suffix are the same, we care. Whereas like the next thing we would try is AB and then BA, which aren't the same. So we know that we're never going to run into a world where any word equals both the prefix and the suffix of this word, because the prefix and the suffix are not equal. So we just immediately continue. That shaves a corner, saves some time. And we keep going and we say, okay, try every length of prefix all the way up to, you know, AB, 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 A, every length of suffix all the way back. Try all of those, see if they're equal. If they are equal, then look at all of the words that we've already hashed and see if the prefix slash suffix, because they're the same, equal that. See if we've encountered this exact number, this exact word before, or this exact prefix as a word in the past. So for example, we would say, okay, have we seen an A? Yes, we have. So then we would, our prefix array, our counter, would have included that A in a previous iteration of the loop. So then we add 1 to the res. When we have AB, that doesn't equal BA, and we haven't seen either of those words. But when we have ABA, this hash equals this hash, and also we've seen this word in the past. So we would add 1 there as well. Yeah. And then in the end, we just return the result. So you're sort of combining two things here. The first thing is like this prefix hash strategy, which I love. It makes so many things obsolete. KMP, Z functions, forget about it. Those are a thing of the past. And I actually really want to do a video just on prefix hashing and sort of the interesting math behind it. I don't think it's the world's most complicated thing. And it's much, much less complicated than having to learn a lot of stupid algorithms that you're probably never going to see in a job interview, and you're certainly never going to see anywhere else. So prefix hashing is OP. The second thing sort of here to recognize is that you have to have this frequency counter of all the words you've seen. That's how you get rid of the, I said earlier, it's like O of n squared times m. The prefix hashing is kind of how you're getting rid of the m. You're collapsing that to a linear time, or I'm sorry, a constant time. O of n squared, if you use this counter and you don't have to check every word before the given word to see if they're prefixes or suffixes, you just say, look at exactly this hash, add the number of times I've seen this hash as previous words. That's taking away a factor of O of n. So all you're left with is just O of n constant time, pretty much. Not actually, I'm sorry, not quite, because you do have this inner loop. And actually this really matters because this question is where that constraint comes in. They specifically say the sum of all lengths of all words does not exceed 500,000. And what that means is, like, if we're iterating through every character and every word, you know, it's not going to go above 500,000. So both of these loops together is only going to be up to 500,000. And yeah, that's really all there is to say about this question. I think it's important to cut this corner. This is a pretty big corner to cut. Another one is there's multiple ways you can hash, and it's always a little bit of a trade-off between whether you want there to maybe be more collisions but it's faster, or it's much slower, like I use a gigantic number but there's a lot less collisions. I lucked out this, I mean, slightly. I didn't hit the 1% chance that there would either be a collision or this would be too slow, so I consider that lucky. That's those two questions. I mean, those were kind of the interesting ones, I guess. Find the length of the longest common prefix. So it's actually quite similar. We have all these numbers and we want to say which one shares the longest common prefix as a string. And that's pretty much what we do. We turn them into strings. And then what I do is I put them in a try. I think that's kind of the intent here. So you put all of one of the array's numbers into a try. A try is kind of just a tree where you're tracing the prefix. So you'd say, like, start at 1. Okay, cool. So we have a 1, so there's something there. Okay, and we have a 1, 0. So from that 1, go to a 0. And then from that 1, or from that 0, go to a further 0. So now you're like 3 nodes down in this tree that you can imagine. And I put all of those into the try. And then here I don't even bother to put the R2 numbers into the try. I just check them against the try. So I say, see how far down you can go. Is there a 1 in the try? Yes. Does that have a 0 as a child? Yes. Does that have a 0 as a child? Yes. Does that have a 0 as a child? No. So there's not a length of 4 match, but there is a length of 3 match. And that's how we get 3. And sort of the part of this problem that's a little bit tough maybe is that both of these lengths could be 50,000. And if they're both 50,000, you can't just brute force check. You can't just say, check 100 against 1,000, check 2 against 4, check 2 against another 4, because that would be 25 times 10 to the 8th, which would be way too big. So you got to use a trie. I think that's kind of the thing to think there. This one, I think, is just a matter of debugging more than anything. It's just sort of like doing what they're telling you to do kind of quickly. They're saying like draw a line starting at any cell, going in any specific direction. You continue going in that direction. That line traces out a number, so like 11 or 19 or 191, and all the numbers along the way, because the line doesn't necessarily like start and end at a wall. So like 19 also encapsulates 1. And add up all of those, figure out what the most common prime above 10 is. And specifically something being a prime or being above 10 seems pretty like just an extra step. It's barely, I would barely even call that a twist. You just have to like have a sieve, or I didn't even do that. I just said like, is the number prime, cache the answer. And then from there, it's just sort of like traversing through a matrix effectively. So I said like, okay, here's all the directions from every single point. Look at every row, look at every column, from every single square. Just draw all 8 paths that you can draw. Find what the number is going to be. So that's Z here. And then just like add that to the counter. And then in the end, I don't even do anything fancy. I just say like, look at every number, look at its frequency. If either the frequency is higher or the frequency is the same and the number is higher, then that's your new maximum, and then return the max number. So all in all, kind of a cool contest, I guess. They seem pretty obsessed with these two-parter questions and also these string questions. Yeah, Q4 was kind of cool. String hashing is not as scary as it sounds. But anyway, I guess this will see the world in 28 minutes.